Alrighty, we're going to go through reaction coordinate diagrams one more time. There's three parts. There's energy, there's reactants, and there's products. We're going to talk about two other parts in a little bit, but the three main parts are energy, reactants, and products.
Alrighty, we're going to go over this graph one more time. On the y-axis right here we have energy. Energy is going up. On the x-axis we have reaction coordinate. You can think of that as time. So at the very start of the graph we have reactants. And at the end of the graph we have products, whatever the reactants combine to produce. In this graph we have a little bit of energy going up and a huge drop of energy going down. And if energy is going up here, this shows that energy is going down. If energy is going down, that means energy is being released, like in an explosion. For example, if I have this firecracker right here, I light the fuse absorbs the energy, and then all this energy is released when the firecracker goes boom. On the other side, here we still have the reactants in the first side of the graph. We still have products at the end, but we see this huge increase in energy. So what this means is that energy is being absorbed. For example, if I have an ice cube and a light bulb is shining on the ice cube, it's going to start absorbing energy. When that happens, this solid ice cube starts to melt. When the ice cube has absorbed all of the energy, it's 100% liquid, or what we call puddle. Our product is a completely liquid product. So y-axis we have energy, reactants at the start, products at the end, change in energy in the middle.
So we said on the x-axis is energy, at the start is products, at the end, at the start is reactants, at the end is products. At the start is reactants, at the end is products. Endo means to take in, so they absorb energy. Reactants should have low energy. Since they're absorbing energy, reactants have low energy, and then that means our products will have high energy. Exo means to exit, so energy is exiting our system. So the reactants must have high energy to start with to be releasing energy, and the products have low energy. These high energy products must be the endothermic graph because they absorbed all the energy. These low energy products must be the exothermic graph because it released all the energy. For enthalpy, that's our change in heat. We find that as products minus reactants. It's going to be positive for endothermic, negative for exothermic.
So another thing that we can get from this graph is the enthalpy. That's our change in heat. If our system is gaining energy, it's absorbing energy, that change is positive, endothermic. If our system is releasing energy, the system is losing energy, that's going to be a negative change in energy. So if we have a graph, we can solve for the enthalpy if we take the energy of the products minus the energy of the reactants. So on this side, if we take this small product number minus our large reactant energy, we're going to get a negative number. So this must be an exothermic graph. On this side, if we take our large product energy minus our small reactant energy, we're going to get a positive delta H, a positive enthalpy. So this must be the endothermic graph. So if you want to solve for the enthalpy, we're going to take our product energy minus is the reactant energy. For example, if we say this product energy is about 60, our reactant energy is 20. That means our change in enthalpy 60 minus 20, we're going to get 40. We'll give us for 10 units, we'll say kilojoules per mole. Let's do another one. Alright, let's say this time our products is 20, because the products is the last part of the graph, and the reactants is 7, that's the beginning part. We do the math, 20 minus 70, we're going to get negative 50. And we'll say kilojoules per mole again for up to 10 units.
So if we say that our products is 40 and our reactants is 10, 40 minus 10 is going to give us 30. This time the reactants is 10, the products is 10, and the reactants is 40. So if we do 10 minus 40, we're going to get negative 30 this time. So this time energy is being released. So this time, even though there's a bunch of squiggly stuff in the middle, that's not important for the enthalpy. If we say that the products is, we'll say roughly 20, and the reactants is 30, 20 minus 30, we're going to get negative 10. We're going to release negative 10, we'll say kilojoules per mole of energy. The last part of this graph is going to be activation energy. That's our energy required to react. We're going to take the peak energy minus the reactant energy. And generally, you're going to have a higher activation energy for endothermic than you will exo.
So the last part of this graph that we need to talk about is the activation energy. That's how much energy we need to start the reaction. And we're going to solve for that by taking our peak energy minus the reactant. Because at the peak, that means the reaction has already started. From reactant, peak is energy that we need to get started, to break bonds, to have molecules move around until they can start making bonds. So here we take this peak minus this reactant energy. It's relatively small, so it's probably exothermic. Exothermic generally release energy, so they don't need a lot of energy to get started. On this side, our peak and our reactant distance is huge. We need to absorb a lot of energy before we can get our products. So that shows me that this is an endothermic graph. Something that needs to absorb a lot of energy before we can get the products. Alrighty, so if you want the activation energy, we're going to take this peak energy, and we're going to subtract off the reactant energy. So for example, if our peak, let's say, is 90, the reactant energy down here at the beginning is 20, and that means that we need 70, we'll say kilojoules per mole to get our reaction started. If we change that up, let's say this peak is still 90, but our reaction energy is already at 70. So this time we only need 20 kilojoules per mole to get the reaction.
So here we can say the peak is 50. Our reactants will say it's 10. 50 minus 10, we only need 40, let's say kilojoules per mole to get started. Here we'll say the peak is still 50 because it's above 40. 50 minus 40, we only need 10 kilojoules per mole to get started. And here we count the peaks, 1, 2, 3 peaks. So this reaction has to be activated 3 times.